In this exploratory demo, I'll describe the components and features of Consul Terraform Sync. Okay, to get started, I've opened my browser, and in the first tab, I've navigated to developer.hashicorp.com/console/tutorials/production-vms/reference-architecture. I'll describe this diagram in a moment, but first, what is Consul? Well, Consul is a tool created by HashiCorp to manage and simplify the networking of services in dynamic infrastructure environments, like those using microservices or cloud-based systems. Core features of Consul include service discovery. The Consul Service Catalog is a core component of Consul that serves as a dynamic registry of services within your infrastructure. It provides a centralized location where services can register themselves and discover other services in the network. Think of it as an address book for your services. When a service starts, like a web app for example, it registers itself with Consul. Other services can use Consul to find it without needing hard-coded IP addresses or DNS entries. Another core feature of Consul is health checks. Consul makes sure your services are up and running. If a service fails, Consul marks it as unavailable so traffic isn't sent there. Consul provides a key value store. This is a place to store configuration data for your application, like API keys, feature flags, or database connection strings. Consul helps manage secure communication between services using a feature called a service mesh. This is especially useful for encrypting and controlling traffic. So why is Consul important? In modern cloud environments where services are constantly scaling up or down and moving between servers, Consul simplifies the process of finding where services are running, ensuring communication between them remains secure and reliable, and keeping configurations up to date automatically. So this diagram presents the recommended architecture for a Consul cluster. The cluster has 5 nodes spread across 3 availability zones. This setup ensures resilience, allowing the cluster to continue functioning even if 2 nodes fail or if one entire availability zone becomes unavailable. These nodes collectively operate a Raft-based consistent state store, managing updates for the service catalog, sessions, prepared queries, access control lists or ACLs, and the key value store itself. A Raft-based store just refers to a distributed consensus algorithm called Raft that's used to manage a consistent and reliable state across a cluster of nodes in a distributed system. This approach ensures that all nodes in the cluster agree on the same state, even in the presence of failures, making it highly reliable for critical operations. Now, what is Consul Terraform Sync? I'll open the second tab where I've navigated to developer.hashicorp.com/terraform/tutorials/networking/console-terraform-sync. Imagine you're managing a lot of services and infrastructure. Some of these services need networking changes or updates in real time, like load balancers, firewalls, security rules, or DNS records, to ensure that everything runs smoothly. Manually updating these configurations can be slow, error-prone, and repetitive. Consul Terraform Sync automates this process by connecting Consul with Terraform. It detects changes in your services and automatically applies the necessary infrastructure updates using Terraform. So this diagram illustrates the architecture of a Consul Terraform Sync implementation running on AWS. Let's break down the components and the flow. First, the Consul cluster. The Consul control plane, or servers, act as the source of truth for service data. The control plane stores the service catalog, handles service discovery, and tracks the health of services running in the environment. The control plane communicates with Consul clients running on the EC2 instances. Now, the application instances. In this diagram, there are 2 EC2 application instances, Nginx 0 and Nginx 1. Each instance has a Consul client running, which registers the application with the Consul cluster and provides real-time information about the application's health and availability to the cluster. Next, we have the CTS EC2 instance. This instance contains the Consul client, which syncs with the Consul cluster to detect service changes, for example, scaling events for Nginx. It contains the CTS daemon. This automates infrastructure changes based on service changes reported by Consul. And Terraform, which executes tasks to modify infrastructure, such as updating security groups. Next, we have the automated task, EC2 security group updates. The CTS instance dynamically updates EC2 security group rules for the jump host instance. Its purpose is to allow SSH access to active Nginx instances, that's Nginx 0 and Nginx 1, based on their status in the console catalog. Now the jump host instance. A jump host instance, sometimes referred to as a bastion server, provides controlled SSH access to the application instances. CTS ensures that the jump host can only communicate with instances that are healthy and registered in console. So a summary of the flow. Console clients report application state to the console cluster. CTS detects service changes via the console client on its instance. Terraform automates infrastructure updates, for example, the security group adjustments, and SSH access to the jump host is dynamically controlled based on current application instances. In the following demos, we'll implement this architecture on AWS infrastructure.